my name is Benjamin and welcome back to my
it
channel,
becomes a
Learn a Lot.
nice-
If you have not subscribed,
nice
this is the time to do it. Subscribe and
nice
hit like,
something.
comment,
and then
and
specify where
share.
I'm gonna save this thing. Gibra. I don't know where I'm gonna save it. This is crazy. Where's my K? Where's my thing? Where I'm gonna save it? Where is my Learn a Lot folder? I save it in Learn a Lot. There you go. So we're gonna save it. There you go. So that's what we have there. So next, what we can try and do is now let's try and call the climate data that we had. We loaded climate data, right? So let's say if we call head climate, the data has got decadal information about precipitation, evapotranspiration, temperature. This is water balance, and then these are the probabilities of these values to occur, and this is an SPI index for each of these probabilities. This tells us that there has been drought, and this tells us that there has been abundance of rain. So the negative values are droughts and the positive values are abundance of rain, right? So I just need these variables. I don't need to include these ones. So I need the first 5 variables. So I'm going to create a new variable here and call it clim, which will take in climate information. I need to take from 1 to 5. Sorry, then I'm gonna run that. If I say head clim, there you go. So I just have didn't I need 5? No, I needed 4 because I don't need the probability one. That's just gonna create noise in our analysis. I just need the first 4. So okay, now that we have this data, I want to combine it with the one that we had. But first, I want to know how much data is there in this claim. We've got about 171. So I want to take the last 32 points from 171. Let's see. If I say, if I say 171 minus 32, so I need to start taking from 140 to 171. I just want to try to see what will happen. I've never done this before. Let's say clean. Let's see if it worked. It worked. So it took the last 32 points and then it took the 4 columns that I needed. Nice. So now we're going to combine this claim with the what you call is the coverage data, if we can call it like that. So we're going to say our ultimate data, or we can actually even override that one. No, but I don't want to override in case I need it. Let's call this one that, which will be cbind, combining the columns, remember, of DTA with climb, right? Yeah. I remember we converted this thing to matrix, so I think we need to convert it back to data frame. Is I want to convert it back to data frames to avoid issues. So now we've got that. So we've got all 7 variables. So I want to try do a bit of principal component analysis to see if we were to run a model to identify the reasons of these changes that we observed in our plot. Looking at the climate variables to see which of these variables affect these variables the most. We'll try and use probably principal component analysis to identify the most important variables, and then later on try and do a correlation analysis to see which one relates more to which variables and all that. So I'm going to go into this script that I've already written here, I'm gonna call these libraries, and then we're gonna look into running the principal component analysis. So I'm gonna give that name. So I'm gonna run that. This should give us a nice, interesting plot. There we go. So we've got this interesting plot here. So you can see that we've got like base soil, which is base soil and temperature, which are working in opposite direction with evapotranspiration and vegetation, which makes sense from our plot. Remember, we talked about how vegetation is interacting a lot with base soil. When vegetation loses information, base soil gains information and all that. And water seems to not interact with any other variable here, but might be increasing when these ones also increase. They might be in the second dimension. In the first dimension, we've got these ones that are interacting more. So we can try and plot the remaining of our uh, variables to see what they give us. So if we plot, let's say the correlation plot, let's plot the correlation plot and see what happens. There we go. So in the correlation plot, what do we learn? We learn that in the first dimension, the most important variables, we've got the base soil vegetation and water balance, maybe water, what's called this evapotranspiration and precipitation. Temperature comes in there, but not that much. Water is practically useless in the first dimension. As we notice, it was behaving on its own. And in the second dimension, you can literally see that water, and like I said, might interact with the two, with the rainfall and water balance. That's why in the two dimension they are there. So this is what I was talking about. If we go back in the previous plot, you see water balance and precipitation might interact with water more and affect it positively more, and these ones are behaving against one another. So now in the plots that we have here, the correlation plot, we can tell that, okay, the most important variables that we'll need for our model are in the first and the second dimension, which is water, base soil, vegetation, evapotranspiration, water balance, and rainfall. We might also include temperature, but I would advise against it because temperature is already used to evaluate evapotranspiration. Since evapotranspiration is already correlating stronger to the other variables, then we don't really need to use temperature per se. I don't know if there's any other interesting plot that I can show you guys, but yeah, this one also shows us a level of importance of variables. You can see that temperature is not really that important. We don't really need to include it into our model. Yeah, not really. I don't really like that plot anyways. So on this one, we got the temperature is not really that important. Even it evapotranspiration, but it's above 70%, so we can actually include that. So we can actually include evapotranspiration, vegetation, water, DP, DH, and base soil, and exclude DT because temperature is just not that important. That's contribution, yes, this is one of the most important. So it can this shows you actually which variables would contribute to your model between if we combine the two dimensions. So we've got water balance, precipitation, base soil, vegetation, and water. Temperature is basically useless, so we can actually discard temperature from our model. Even evapotranspiration as well, I said it, evapotranspiration could also be very much useless. We don't really need it, so we can actually take it out from our model. Uh, let's see. Yeah, well, that's that. The rest is not really important for this tutorial. But as we have seen, we were able to create our plot and detect changes. Okay, this is the, I missed this. How did I miss this plot? This is the one that shows us the percentages that each dimensions contributes. Remember, we identified two most important dimensions, which is 63% and 15%. 63 plus 15, that's about 78%. If you have these two dimensions, you can explain 78% of your data set. The two, so including the 5 variables that we identified in the 2 dimensions, we can actually have 78% of the information we need, or the explanation we need on the behavior of our data set, which is enough. If you ask me, you don't have to have 100% of your information. So if we include base soil, vegetation, DP, DT was not really important, DH and water, we should have all the information we need. So that's that. So but if we choose to include the third dimension, in the third dimension, what do we have? The temperature can become handy in the third dimension, but it's not really important. The two first dimension are already enough for us to do what we need to do. So this is it for this tutorial. I think we are at the end of our change detection analysis using R, a numerical expression or a numerical point of view. I hope you enjoyed this tutorial, and if you did, please like and share, and also subscribe to my channel. Until we meet again, stay frisky. Ciao, your boy Benjamin was here.